Right, this is a lecture on the Kronecker delta and Levi Civita symbols. Right now, first off, definitions. This is the Kronecker delta, and as you can see, it's the delta symbol with a lowercase jk. Now, this is equal to 1 if j equals k, and 0 if j does not equal k. And what we do with all these values that we'll see on these slides is we sum them between 1 and 3. No, I mean they have values between 1 and 3. But if a value is repeated, then you sum it between 1 and 3, rather than take values. So because it's 1 and 3, this will give us the identity matrix. And properties, you can reverse the identities. So we'll have delta jk equals delta kj. If we have doubles, like I said before, we have delta jj. We sum them, remember, so we'll have delta 1, 1 plus delta 2, 2 plus delta 3, 3, which will be 1 plus 1 plus 1, which is 3. And if we have an index repeated in the middle, so it's together, then delta jk times delta kl will equal delta jl, so we just remove the k's. Next one, this is the Levi Civita, and it's just the same as the other one, but instead of being a 3x3, it's a 3x3x3, so it's a cube. And this has values 1 if jkl equals 1, 2, 3, 2, 3, 1, or 3, 1, 2, it's just a cycle. Minus 1 if jkl is 1, 3, 2, 2, 1, 3, or 3, 2, 1, again it's just a cycle again. Or 0 if it's anything else. And we can lay this out like this. So I've got each of the screens here, so it's like a cube. So this is L is 1, L is 2, L is 3, different planes. And we have J down there and K across there. So if we have J is 3, K is 2, and L is 1, 3, 2, 1, we'll get minus 1. And that's how that works. Some properties. I don't know if this is a bit small or not. We have epsilon jjl is epsilon jlj, so epsilon ljj is 0. If any indexes are repeated in the Levi Civita, then it's automatically equal to 0, because we have none of these repeated, do we? If you want to swap any of the, if we wanted to swap j and k, for instance, then all we do is we multiply it by a minus. So epsilon jkl is minus epsilon kjl, and that's minus epsilon jlk. And if we were to swap two things, so jkl is klj. If we were to swap two things, here we've swapped j and l and then k and l. Then obviously it's a minus and then a minus, so it's just a normal plus, so nothing happens to the sign of it. One of the things, which is, I think it's something to do with the determinant, is that if we have the same value in the middle, so here we've got epsilon jkl, epsilon lmn, so we've got ll, then we can write this out using the Kronecker deltas as delta jm, delta kn minus delta jn, delta km. I think of it as the first one times the middle, the second one times the last, minus the first times the last, the second times the middle. It just shuffles along like that, and then back it goes. That's how I think of it. Think of it how you like. The cross product, A cross B. Now J, this is the jth component. So we've got I, J, and K. We'll have epsilon jkl ak bl. Yeah, so that's what that's equal to, which we'll find useful. And for the dot product, a dot b is aj bj. And again, if you remember, we're summing them if there's 2 between j is 1 and 3. So it'll be a1b1 plus a2b2 plus a3b3, which is the dot product. Questions. Right, I've got the rules down here to help. Show that a dot b cross c equals b dot c cross a. Now we've got this rule here and this rule here. So we'll have AJ, let's show it here, AJ, and then the rest of this, because our B is just being replaced by this. So it's AJ epsilon JKL BKCL. I hope you can see that. And then all we want to do now is we want to rearrange it into a form that looks like this. So I've put the B in front, and we've got AC, and then we'll have to swap the C and A. So we've got BCA. Now this is not yet in the correct form we need, because we'll need it to look like this. So we'll have to have the K, we'll have to have the L as the middle term, and the J as the last term. So we'll have to do some rearranging of this epsilon. So if we want the L in the middle, we do one swap, which will give us a minus. And if we want the J at the end, then we'll have to do another swap, so it will still be positive. So we'll go to minus epsilon JLK, then swap it again. We'll have epsilon LKJ. KLJ, yes. And then this, of course, is just equal to this, because this is the cross product of C cross A, and this is just the dot. Next one, show that epsilon JKL epsilon KLM is equal to 2 delta JM. Now, first thing we want to do is we want to get this into a form like this, because this will be very useful because we've got deltas. So we need to get the middle terms equal. So we can perform one swap here to make it epsilon LKM. So it'll be minus this. Yep, so we do one swap. And then we can write this in a form like this. I've just put the minus outside, and we've got delta JK delta KM minus delta JM delta KK. And like we've said in the original Kronecker delta slide, if it's repeated, then it will equal 3. So we'll have a 3. This JM is fine. And here, because it's in the middle, we've got K then K, then we can just get rid of it and have delta JM. So we'll have minus delta JM. This minus will become a plus delta JM times 3, which will equal 2 delta JM. I hope that made sense and that you can see it.